In the frigid reaches of our solar system, where the sun is just a bright star in a black sky, spins one of the most overlooked and underestimated planets, Uranus. At first glance, it appears serene, a smooth, aquamarine orb, seemingly devoid of detail. Compared to the dramatic bands of Jupiter or the rings of Saturn, Uranus has long seemed uneventful. But now, scientists are beginning to understand that behind that calm facade lies a restless, dynamic world, a place where storms erupt silently, clouds form and vanish without warning, and vast, swirling dark spots appear in the deep atmosphere before fading again into obscurity. With new data from the Hubble Space Telescope, high-resolution simulations, and comparative studies of ice giants, we're finally peeling back the hazy veil of this pale planet. What we've discovered is rewriting our understanding not just of Uranus, but of how weather behaves across the solar system and beyond. In 1986, NASA's Voyager 2 spacecraft became the first and only mission to fly past Uranus. It offered humanity its first close-up images of the distant ice giant. But what it found surprised scientists. The planet looked almost featureless. A pale blue-green sphere, smooth and still. Compared to Jupiter's violent storms and Saturn's swirling bands, Uranus seemed asleep. But there were caveats. Voyager's visit was brief, just a flyby, and it occurred during southern summer, when Uranus's south pole was bathed in constant sunlight due to its extreme axial tilt. The orientation may have hidden active weather near the unlit northern hemisphere, and Voyager's cameras, while advanced for their time, simply couldn't capture fine atmospheric details through the planet's thick haze. So for decades, Uranus was treated as a quiet, largely inactive planet. But that assumption would not last. In the 2000s, as Uranus inched closer to its equinox, a moment when both hemispheres received sunlight, something changed. Telescopes on Earth and in space began detecting subtle patterns, faint bands, drifting cloud systems, and, eventually, large, dark ovals forming within the planet's cloud decks. In 2006, the Hubble Space Telescope captured one of the first clearly defined dark spots in Uranus's atmosphere. Unlike Jupiter's Great Red Spot, which towers above surrounding clouds, Uranus's dark spots appear to be depressions, vast, swirling vortexes where gases circulate in high-pressure systems, revealing deeper, darker layers of atmosphere. These weren't rare blips. In 2012, 2014, and most clearly in 2018, Hubble observed similar features, all changing position, depth, and surrounding cloud formations. The once quiet Uranus was now revealing a complex, active meteorological system, and each storm brought with it a deeper question. What creates these dark spots? And what do they tell us about the deep atmosphere of an ice giant? To the human eye, Uranus appears a uniform, icy blue, but dark spots disrupt that illusion. They are typically elliptical or circular depressions, spanning thousands of kilometers. Hubble's observations have revealed spots nearly 7,000 kilometers wide, roughly the diameter of Earth. Some are bordered by bright, white methane clouds, which form where air is rising and cooling around the edges of the vortex. But inside the spot, there is still mystery. Unlike Jupiter's colored storms, Uranus's spots are thought to be optically dark because we're seeing deeper into atmospheric layers where sunlight is absorbed, not reflected. These layers are warmer, more turbulent, and possibly rich in different chemical compounds. The storms are likely anticyclonic systems, high-pressure regions where gas circulates counterclockwise in the northern hemisphere. They don't just hover, They migrate across latitudes and can weaken or dissipate entirely. Some fade within weeks. Others last for years. But always, they hint at a deeper truth, that Uranus is not quiet. It's simply been hiding its weather systems beneath a thick, obscuring haze. To understand the behavior of these dark spots, scientists have turned to fluid dynamics and planetary simulations. What they've found is both strange and familiar. In many ways, Uranus shares characteristics with other gas and ice giants. A fast rotational period, just over 17 hours, internal heat flow, and a deep atmosphere composed mostly of hydrogen and helium, laced with methane. But unlike Jupiter and Saturn, Uranus emits almost no internal heat. Its interior seems unusually quiet. This lack of heat poses a problem. Where does the energy for storm systems come from? Some researchers propose that seasonal changes, driven by Uranus's extreme tilt, may create gradients in sunlight that build up slowly over decades, eventually sparking storms when conditions align. Others suggest that latent heat from deeper atmospheric layers may occasionally rise in bursts, forming vortices. In either case, once a vortex forms, it behaves like a planetary hurricane, spinning, pulling surrounding gas into circulation, sometimes creating bright companion clouds of methane as air is lifted and cooled around the spot's edges. These systems are not passive. They move, they evolve, and they disappear, leaving behind only questions and trace signatures in the clouds. Why does any of this matter? Because Uranus and Neptune represent a class of planet that is common across the galaxy. In fact, ice giants, planets between 2 to 4 times Earth's size with thick atmospheres, are among the most frequently detected types of exoplanets. Yet in our own solar system, we've studied these planets less than any others. What we learn about dark spots, storms, and atmospheric chemistry on Uranus will directly inform how we interpret alien worlds. Do similar dark storms exist on Neptune analogs in other systems? Do high-altitude clouds reflect different heat signatures? Can a spot like this form on a planet with no internal heat source? The answers lie with Uranus, and perhaps someday soon, with a dedicated orbiter mission, we will descend through its cloud layers and see these mysterious vortices up close. As Uranus tilts toward northern summer, a new face is turning toward the sun. More of the planet is becoming visible. Already, telescopes are detecting more active weather, stronger bands, and new transit features. It's as if Uranus is waking up from a centuries-long slumber. And with that awakening, scientists are eager to catch each storm, each flare of methane, each dark spot, knowing that they are watching something rare and fleeting unfold. For the first time, we're not just observing Uranus. We're listening, we're learning, we're decoding. The planet that once appeared still is now anything but. In the end, the great dark spots of Uranus are more than meteorological phenomena. They are the fingerprints of a living atmosphere, volatile, layered, evolving in cycles that span decades. They remind us how much we have yet to discover, even in our own cosmic backyard. And as new technologies emerge, more powerful telescopes, better simulations, and perhaps one day, robotic explorers, we may finally descend into those veiled cloud tops and see, with clarity, what has hidden in plain sight for generations. Until then, we continue to watch from afar, catching glimpses between the shadows of a giant world still cloaked in mystery.